I am Ziyu Xiao, from University of Science and Technology of China. I would like to introduce our work, CutMIB, Boosting Light Field Super Resolution via Multi-View Image Blending. Data augmentation is an efficient strategy for improving the performance of deep neural networks. Recent DA strategies have demonstrated utility in single-image super resolution. Little research has, however, focused on the DA strategy for light field super resolution, in which multi-view information utilization is required. For the first time in light field super resolution, we propose a potent DA strategy called CutMIB to improve the performance of existing light field super resolution networks while keeping their structures unchanged. Experimental results demonstrate that CutMIB can improve the reconstruction performance and the angular consistency of existing light field super resolution networks. We further verify the effectiveness of CutMIB on real-world light field super resolution and light field denoising. Light field describes the intensity of light rays emitted from different spatial positions in a scene and in different directions. Compared to 2D images, light field provides information about the scene from different angles. By capturing the direction and intensity of light rays, the light field can offer a more comprehensive description of the scene, enabling observers to perceive the position, shape, and depth information of objects in the scene. Light field imaging technology has wide applications in various fields such as biomedical imaging, industrial quality inspection, and underwater exploration. It offers significant advantages in capturing and analyzing complex 3D scenes, enabling enhanced depth perception, improved image refocusing, and advanced post-processing capabilities. However, due to the limitations of existing imaging technologies, light field images tend to have low spatial resolution, which limits the application of light field images. Most of the existing optical field super-resolution methods focus on designing better and more efficient structures for extracting both spatial and angular information. Despite these improvements, few works have investigated data augmentation strategies for light field super-resolution, which can improve the model performance without the need for additional training datasets, given that obtaining these light field data is often time-consuming and expensive. Data augmentation is an efficient strategy for improving the performance of deep neural networks. DA has been well studied in high-level vision tasks, for example, image recognition, image classification, and semantic segmentation, for achieving better network performance and alleviating the overfitting problem. For example, as one of the pioneering strategies, Mixup blends two images to generate an unseen training sample. The effectiveness of the DA strategy on light field super resolution has received very little attention. As a pioneering work along the line of DA for low-level vision, Feng et al. Analyze mix-up in single-image super resolution to suppress the model overfitting phenomenon. The paper most related to us is CutBlur, in which a comprehensive analysis of the existing data augmentation strategies is applied to the single-image super resolution task, and a novel data augmentation strategy called CutBlur is proposed. In addition, CutBlur shows promising results in image denoising and JPEG artifact removal. Our CutMIB, which is inspired by CutBlur, first cuts low-resolution patches from different views in a low-resolution light field at the same position. The cut low-resolution patches are then blended to generate the blended low-resolution patch, which is then pasted to the corresponding areas of various HR light field views, and vice versa. Therefore, each augmented light field pair has partially blended low-resolution and blended HR pixel distributions with a random ratio. By feeding the augmented training pairs into light field super-resolution networks, these networks can not only learn how and where to super-resolve the low-resolution light field, i.e., benefit from the cutting blending operation, but also utilize the implicit geometric information in multi-view images, resulting in better performance and higher angular consistency among super-resolved light field views. We can observe two phenomena from the table. 1. The views along specific directions do not matter in CutMIB. although the implicit geometric information of these views is practical in other tasks. As can be seen from the table, various views along different directions remain the same as the final results. 2. Involving more views yields better results. This is consistent with our common sense, because more SAIs can provide more implicit geometric information during the training stage. We first test our proposed CUTM-IB and CUT-BLUR on various benchmark datasets in the above table. The table shows that as compared to CUT-BLUR, the networks trained with CUTM-IB achieve greater reconstruction performance. Here we show quantitative comparisons of the methods trained without and with CUTM-IB on benchmark datasets. The table shows that existing light field super-resolution networks trained with CUTM-IB outperform the corresponding baselines by a considerable margin. Specifically, on 4-time light field super-resolution of HCNU, ATO trained with CUTM-IB achieves 30.950 dB, PSNR, while the same network trained without CUTM-IB only gets 30.813 dB, PSNR. Qualitative results on ×2 and ×4 light field super-resolution are presented in the above figure. It is clear that the networks trained with CUTM-IB provide better qualitative results than their baselines, with more accurate details and fewer blurs. As can be seen in the above figure, the disparity maps estimated by the results generated from the networks trained with CUTM-IB have sharper edges and more accurate results, indicating the effectiveness of our CUTM-IB. We validate the effectiveness of CUTM-IB on the light field denoising task. As can be seen in the table, all the methods trained with our proposed CUTM-IB achieve higher reconstruction fidelity than their baseline versions, validating the advantage of our CUTM-IB. We also conduct experiments to prove that networks trained with CUTM-IB can generalize well to real-world light fields. We choose a real-world light field from the HFUT dataset, and we super-resolve this light field directly using the baseline networks and their corresponding versions trained with CUTM-IB. Here comes the conclusion of our paper. For more results and algorithm details, please read our paper. Thank you for your listening.